All right, so today we're going to be finishing up weather theory. This is part two of the weather theory episode series, I guess. Watch part one. Make sure you get a good base so you understand what we're going to go ahead and be talking about today. We left off on talking about how we cool an air parcel via adiabatic cooling as it goes up and up into the atmosphere. Cools, cools, cools. If it is warmer than the surrounding ambient air temperature around it, it will continue to rise. And if it's colder, it will stop rising. However, if the lifting mechanism or the lifting method is severe enough, it doesn't matter if that air parcel is colder than the air around it, it will continue to rise. You know, if we go back to vertical motion, what are the three different methods? First one's thermal. Heating of the Earth's surface, raising that air parcel, cooling it, condensing it. Orographic lifting, which is pushing up a mountain slope, traveling through the topography of the land, cooling it, condensing it. And then we have frontal lifting, which is where we're going to kind of start off here, is talk about fronts and how air masses actually meet, collide, interact with each other, and raise air parcels. But the main thing I want to talk about that I know I did not mention in the first video is, you know, if that air parcel is cooler, if that if that lifting method is severe enough, it doesn't matter. We'll continue to rise, making thicker and thicker clouds or more severe weather phenomenon. So we'll start with air masses. How do air masses actually form? Well, they form all across the globe. With similar properties. You know, it always happens when the surface has an equal temperature to the air above it. So if we think like deserted wastelands, not a lot of horizontal movement going on, or if we think of air over the ocean, we think moist air, probably cold. In some instances, it could also be warm and moist as well. Now, we also talked about how horizontal movement is all about the uneven heating of the Earth's surface. So we always have high pressure air seeking out low pressure areas, and the Earth is in a constant state of trying to reach this equilibrium, which it never will. So as these air masses move over the Earth's surface to seek out those areas of low pressure, they come into contact with one another, and they pick up certain properties from different air masses along the way, creating all sorts of weather as they travel across the Earth. So that's going to be the backbone of weather system formation. There's going to be, 6, 7, 8 different types of weather systems. They all have, we have cold, dry ones. We have cold, moist. We have warm, moist. We have warm, dry. All these different ones. You don't have to memorize those. Just have a good understanding of how those actually form. It's just the land having similar properties to the air above it. Now, what happens when these air masses actually meet? They come into contact with each other. The leading edge, the point at which they actually hit one another, is going to be called a front. And this is how we get that frontal lifting, how we actually raise an air parcel into the atmosphere, cooling it, condensing it, and then precipitation occurs. So be 4 different types here. First one is going to be a warm front. So warm front, we can kind of just imagine we have this air mass that is low pressure, not very dense air, coming into contact with high pressure cold air. As it's traveling this way, what do you think is going to happen? It can't push up, this high pressure air mass. It's too dense, it has nowhere to go. So if we're getting winds that are forcing this air mass, this low pressure air mass this way, it's going to go ahead and rise over. And the point in which they meet is actually going to be the front itself. So as this warm, moist air goes over this high pressure air mass, it's going to create some weather because we're raising an air parcel here, cooling it to a point where it reaches its dew point and condensation occurs. However, with warm fronts, we actually get a little bit more stable air, creating some sort of like temperature inversion, because we're putting warm air higher in the atmosphere. We can get severe weather. You can still get those thunderstorms. You can get severe turbulence, maybe. You can get showery to continuous precipitation. Good visibility. It could also be poor as well. So it's kind of not as severe as the cold front we're going to go ahead and be talking about. There is a stability feature to the warm front, however. And we also get some, layer-like stratiform clouds with these warm fronts as well. Now let's talk about the cold front. So cold front, we can kind of think of it like a bulldozer. We have high pressure air coming to meet low pressure air, so just the opposite. What do you think is going to happen here as this high pressure air goes this way, this more dense air? It's going to go ahead and come into contact with this low pressure area, and it's just going to go ahead and send it aloft. And depending on how fast this cold air mass is actually moving, it can do it pretty drastically. And when it does that, once this high pressure air goes under, lifting this warm moist air aloft, we can get some pretty severe weather. This is where we get, potential squall lines, just a row of thunderstorms. We have embedded thunderstorms. We get severe turbulence. You can also get wind shear, microbursts, stuff like that from this cold front's happening. So just kind of imagine that cold front as, a bulldozer, just high dense air, just pushing past that low pressure area and sending this warm moist air aloft. Then we have the stationary front. So we have two air masses here that have properties of, a high pressure air mass and a low pressure air mass. These two air masses come together, they meet. What's going to happen? It really depends. So we have a high/low pressure air mass, another one, or we could have two high pressure air masses coming together. We could have two low pressure air masses together. Who's going to win the fight here, pretty much? And it can really go either way. There's not a lot of movement. They meet and they stay stationary. They don't move anywhere. Nothing's really getting sent aloft too much, depending on the stability of that atmosphere. So they have properties of cold and warm fronts when these stationary fronts actually happen. It can really depend on how stable the atmosphere is for the given day. You'd have to look at the ambient lapse rate, which we talked about varies day to day. But if it's stable, it's kind of neat, and it can create really good weather conditions for a day. And if it's unstable, it's going to go ahead and send it aloft, and we can get some precipitation, we can get turbulence, we can get different wind speeds, stuff like that. But it really depends on what that ambient lapse rate is and how it's stable that atmosphere is. And then the last one here, we have an occluded front. And these are kind of misunderstood. There's going to be two different types of occluded fronts. First one's going to be a cold front occlusion, and the next one's going to be a warm front occlusion. So, cold front occlusion, just remember, this is going to be the most severe type of weather. We have a high pressure air mass coming into contact or catching up to a warm front. So we have a low pressure air mass that's going over a high pressure air mass. So we remember warm front, low pressure air, rising over that high pressure dense air. However, this air mass that's behind this warm front is very high pressure, and it's much colder than the cold air mass already being experienced inside of that initial warm front. So as this very high pressure system comes in, it just bulldozes it and sends them both aloft, creating a very unstable atmosphere, a crazy high lifting mechanism, and that's where we get our most severe type of weather with these guys. The warm front occlusion is going to be warm air. So we have low pressure air coming into contact, catching up to a already existing warm front, but as it comes across, this low pressure air is much lower than the low pressure air already being experienced inside of that warm front. So what's it going to do? It's going to go ahead and rise over both of them. Just shoot up into the sky over them because it's the lowest pressure and it's the least dense. This can create a lot of severe weather as well, more severe than possibly the cold front, depending on the stability for the given day. But always going to be some sort of precipitation occurring here, change in wind speeds, turbulence, showery to continuous precipitation, and all. So unfortunately, we cut out for a second there. We're just wrapping up fronts. Just remember those 5 different types of fronts. We have the warm front, cold front, stationary front, a cold front occlusion, and then a warm front occlusion. Those are all going to be depicted on the surface analysis chart with different colors, so make sure that you understand those. When you go into your check ride, there is a 90-95% chance that you will be asked to pull up one of those charts and let your examiner know via the color identifier what kind of front that is. So make sure you really understand those as well, which we'll go a little bit over what those actually look like when we get to weather information, which is going to be probably the next video coming out. Now, let's talk about types of clouds. We have high clouds, middle clouds, low clouds, and clouds with vertical development. High clouds, we don't really fly at these super high altitudes. You could get some sort of clear air turbulence if you are flying that high, associated with a jet stream, but nothing, too concerning there. We have middle clouds, which, middle of the atmosphere. I believe the actual altitude for it is going to be 6,500 to 13,000 feet AGL. And then the really concerning one is the low clouds. We're VFR pilots. We want to stay VFR. So understanding that a low cloud exists would obviously restrict our ability to remain VFR. We would be in a dangerous position, one, and two, it's illegal. And then we have clouds with vertical development, giving you a signal that there is some sort of instability going on. Probably thunderstorm activity is going to exist, or a really thick cloud as well that you could possibly fly into. When we talk about clouds, there's going to be 2 or 3 different prefixes. So we have stratus. This is, your stratiform clouds. Think a sheet layer, stable. I believe that's the Greek translation. Could be another language, I'm not too sure, Latin or Greek. Stratus, stable, and then we have nimbo, which means rain. Nimbostratus would be a rain cloud. And then we have cumulus, which I believe means unstable. So think thunderstorm activity. So out of all these different clouds, different ranges, high clouds, we get those cirrus clouds, spelled like this. We have cirrus stratus, cirrus cumulus. We have just cirrus clouds, and those are going to be those really high altitude wispy clouds that you see up in the sky. There's a bunch of good depictions on that. Just Google these guys and get that visual representation of what these actually look like. Then we have our middle clouds. We have alto, which is going to be the prefix for all the middle clouds. Alto stratus and alto cumulus, middle clouds, cumulus cloud, little bit of vertical development on it. And then we have the stratus, alto stratus clouds would be that, sheet layer almost, that middle range, no higher than 25,000 feet AGL. And then we have low clouds here, which is where we get the prefix stratus. We have just stratus clouds. We have stratocumulus, which, low clouds with a little bit of vertical development. And then we have nimbostratus clouds, which is those rain clouds at low altitude, which could obviously affect your visibility. So when we talked about these hazards in the very beginning of the last episode, these are those low visibility hazards. So we want to be making sure if we're flying low and we got a low cloud that we divert one. If we are IFR, rated and we have an IFR capable aircraft, go ahead and get that ATC clearance. Or 3, cancel the flight and just live to fly another day, because that is a very dangerous situation that could kill you. And then we have clouds of vertical development. You kind of imagine these huge clouds, thunderstorms. There could be thunderstorms that live inside of these clouds and they're embedded so you can't actually see them. So we really want to understand whenever we have any sort of vertical development with clouds, that there is some sort of instability going on. There's going to be severe turbulence, hail, lightning, embedded thunderstorms, squall lines, all those guys, all those things that we want to stay away from for the most part. And these can range starting in the low clouds and then go all the way up to high clouds, all the way up to the tropopause, that lid on top of the troposphere. So we want to be conscious of that when we're flying around. So those are going to be the clouds there. Let's go into turbulence now. A few different types of turbulence. Turbulence, for the most part, is just going to be air seeking out that low pressure. So we get a different change in direction or wind speed in the atmosphere because of turbulence. First one is going to be convective. Convective turbulence is going to be associated with thermals. So when we think convection, we think thunderstorms. Not in this case, actually. It's just air being heated by the Earth's surface from the sun, rising up, and that's why we get those crazy updrafts and downdrafts when we try to fly in the afternoon on a hot summer day. Super bumpy, hard to hit standards on maneuvers because of convective turbulence. Next one we have here is mechanical. And this is basically the air creating low pressure systems because of obstructions on the ground. So trees, buildings, anything like that is going to create some sort of mechanical turbulence. If you look at the airplane flying handbook, they have a couple good references for images for mechanical turbulence. We have two different buildings creating all these swirly winds inside of it. So as this air hits it, it's kind of a gamble where that wind is going to go ahead and end up. Is it going to go in an updraft? Is it going to shoot to a tailwind for you, a headwind for you? It really depends. So that's going to be mechanical turbulence, just the air coming in contact with objects on the ground, trees, buildings, stuff like that. Then we have wind shear, and then we'll wrap up with clear air turbulence and mountain waves. Wind shear is going to most commonly be associated with a temperature inversion or convective activity. So we think thunderstorms, we think of air rising and downdrafts occurring as well. When we get into the life cycle of a thunderstorm, it can create a lot of unpredictable wind velocity changes or wind direction changes. The definition of a wind shear is going to be any drastic change in wind speed or velocity anywhere in the atmosphere. If we think about that at high altitude, yeah, altitude is our best friend in that case, and it's not really a cause for concern. But when we're approaching and landing at slow speeds, or taking off, or departing from an airport at these slower speeds, if that headwind drastically switches to a tailwind, we're going to decrease performance drastically as well. And you might not have enough altitude to go ahead and get that airspeed back, to go ahead and climb away on takeoff or go around in the event of wind shear as well. So we have to be cautious of that. Next one's going to be clear air turbulence. When we were talking about those high clouds up in the atmosphere, we have free-flowing air that is just pretty much affected by the Coriolis force, and it's really fast winds. Sometimes that creates these pockets of air, low-pressure areas at altitude. High pressure seeks out that low pressure, and it goes ahead and changes the wind velocity or speed. So we got to be cautious of clear air turbulence if we're flying at high altitude, but at the end of the day, altitude is your best friend in that case, and it's not really a cause for concern. And then we have mountain waves here, so wind being affected by the topography of a mountain. So if we have wind pushing up this mountain, on the leeward side of the mountain, it gets very turbulent. And if we go ahead and try to fly an aircraft over this mountain, we can get insane, crosswinds. We can also get insane tailwinds to push us back into this mountain. And we probably won't be able to climb over it as well because the performance decreased drastically. So that's why, if you ever want to do some mountain flying, there's a whole class to go ahead and get that done. So we got to be cautious of that. Mountain waves, topography of the land on that leeward side of the mountain, getting very turbulent. If we're trying to fly over this mountain, it could decrease our climb performance drastically. So being cautious of that. That's going to wrap up turbulence there. Now let's talk about thunderstorms. Why do we want to avoid thunderstorms? Well, turbulence, visibility, lightning, hail, all that stuff we have to be actively avoiding when we're flying around. There's going to be 3 different stages of a thunderstorm. First one is going to be the cumulus, then the mature, and the dissipating. So before we get into this life cycle, what ingredients do we need for a thunderstorm to actually happen? Well, we need water vapor, so sufficient moist air. We need a unstable lapse rate, and that's how we talked about earlier, that ambient lapse rate for the given day. What's an unstable one? Well, anything more than 2 degrees Celsius. And then the third thing is going to be a lifting mechanism. Think thermal lifting. We can get orographic lifting, and then we can also get that frontal lifting. So those would be 3 different options we have as far as lifting is concerned. Now, first stage, the cumulus stage. This is going to be updraft. So we have moist air rising up because of whatever lifting mechanism it was. Say it was a cold front or a warm front, or it was getting pushed up a mountain slope, or we had thermal lifting pushing these air parcels up. Now it's going to get to a point where these, the air parcels that were risen up, this warm moist air, actually condenses. It gets past its dew point and precipitation occurs. Now we get downdrafts, this mature stage. This is when precipitation begins to fall. Then we have the dissipating stage, which is where this thunderstorm starts to bleed itself out. All the moisture that was sent aloft condenses and now is falling to the earth, and it's basically dissipating. Now, why is this such a concern for us? Well, if we're flying through this, we're going to get crazy updrafts, we're going to get crazy downdrafts, we're also going to get restricted visibility, there can also be lightning in here, and we can also get hail. These are all ingredients to really damage your aircraft and potentially kill you. So we have to understand whenever we're flying within 20 nautical miles of a thunderstorm that we actively avoid them. The FAA does recommend to stay more than 20 nautical miles away of thunderstorms. I would recommend 50 nautical miles away, but that's just my personal minimum for it. Thunderstorms are no joke. If you ever experience yourself flying towards a thunderstorm, do a 180, get out of there. Contact ATC, see if they can divert you around the thunderstorm. Never just try to fly through it. But if you do get caught in it, slow down below your maneuvering speed and just try to maintain a constant pitch attitude, try to remain at level, and just accept those altitude deviations within the thunderstorm. Cool. Types of thunderstorms here. We're going to have single cell, multi-cell, and supercell. So single cell thunderstorm is just kind of like this one depicted. We had an updraft, we had a downdraft, and it just bled itself out. And then we have a multi-cell thunderstorm, which is going to be different thunderstorms around each other in different life cycles. So one could be in the updraft stage, the other one could be in the downdraft stage, and they basically feed each other pretty much. And then we have a supercell, which is just a huge thunderstorm cell that when it has downdrafts, it feeds itself new updrafts, and it just keeps feeding itself like that. Most commonly, thunderstorms are going to be some sort of multi-cell. The single cell and the supercell are pretty rare. Yeah, those are going to be the three different types there. In summary, we just have to understand we want to be avoiding, at minimum, these thunderstorms by at least 20 nautical miles because of all those hazards like hail, lightning, wind shear. And one that we have not discussed yet is microbursts. So microbursts are going to be a series of intense downdrafts within a thunderstorm cycle. So we have this uplifting action, and then we have these intense downdrafts that can reach up to 6,000 feet per minute. We're talking about microbursts now. As this microburst comes down, it has a tendency to fan all the air around it out. So this downdraft comes down, fans out, pushing all this air out. If we're an aircraft flying this way, we're going to go ahead and get better performance because we're experiencing a headwind now. So, we want to maintain altitude. We're going to go ahead and pitch the nose down, maybe take some power out, we're like, wow, we have such a good headwind right now. We're staying aloft, and we have to go ahead and configure our power to go ahead and maintain altitude. As we get inside of here, that's when we start experiencing those downdrafts of up to 6,000 feet per minute. And we're like, what the heck? We're sinking like crazy. We're getting drastically close to the ground. Well, just wait. It gets even worse when we get on the other side of this, because now we start getting downdrafts, but we're also starting to pick up a tailwind as well. So we're not accelerating as much air over the wings, and we're decreasing our performance, and we were already drastically close to the ground when we were in the middle of this microburst. So microbursts are going to be associated with intense downdrafts of some thunderstorms, up to 6,000 feet per minute. Best to assume that whenever we're flying around a thunderstorm, we can experience some sort of wind shear or microburst potentially. So that's why we want to avoid them by at least 20 nautical miles. Use 50 on your check ride, though. Tell your examiner that. Yeah, that's going to be microbursts in general. wind shear as well, which is going to be a type of microburst. This is a drastic change in velocity and direction of the wind, which essentially is a microburst. Intense downdrafts, changing from a headwind to a tailwind as we're flying through here. So wind shear, no fun. We're already at a low altitude when we were in the middle of this, and then on the other side we got that tailwind, and we're drastically close to the ground now. So, cool. Wind shear there. Let's talk about frost. So we'll talk about frost, icing, and then fog, and we should be done with weather here. So first one, frost. So how does frost actually create a hazard for us, and how does it form? This is basically ice crystals on the ground or on objects like our aircraft on the ground that can decrease our lift, can change the aerodynamics of the wing, and also increase weight. That's why if we ever have frost in the aircraft, we have 3 options. We can use de-icing fluid. If you're at an airport with de-icing fluid, 1, it's super expensive. 2, you're flying a Cessna, and this isn't a chartered aircraft. We don't need to be at point B today. Do we really need to make this flight? Probably not. What's the point in spending all that money on de-icing fluid? But it is an option if you're at an airport with that. And other one is going to be park in the sun. So we can move the aircraft to a point of the airport that's getting direct sunlight and hopefully melt off some of this frost from our aircraft. And then the third one is going to be a heated hangar. So if you're rich enough to have a heated hangar, good for you. Park it in there, get that frost off, and then you can go ahead and take off. If we take off with frost, it's going to go ahead and drastically decrease our lift. We're flying at slow airspeeds when we're departing, and if we're flying our normal airspeeds, those normal airspeeds might not be so safe. When we get into ice, it's kind of the same story. So frost, it's no joke. We got to make sure that's removed before flight. How does frost actually form? So if we have the ground surface here, at night, the ground radiates heat out into space faster than the surrounding air. So the ground gets cold, much colder than the surrounding air. As this ground gets very cold, as it radiates all this heat into the atmosphere, it also cools the air above it. And if there's any moisture inside of that air, it will cool and condense and fall as precipitation, very low to the ground. If this air is warm, if the air is warm, it will go ahead and fall as dew onto your aircraft, which isn't as severe as frost. But if you're in below freezing temperatures, when this air parcel actually condenses, we will experience frost, and it'll be ice crystals on your aircraft. And this is usually early morning stuff when, after night, we radiate all this heat out, cooled and condensed the air around it, and then we either got frost or dew for the given day. So these are our 3 options here. If we have frost in the aircraft, de-icing fluid if you're rich, park in the sun, and heated hangar if you're rich as well. So it all comes down to the go or no-go decision. Are we going to go ahead and fly an aircraft with frost on it? No, we are not. Are we going to go ahead and get a scraping utensil to go ahead and scrape it off the wings? We are absolutely not doing that. If you have some form of dew, or if you have light frost on the aircraft, yeah, you could probably take a rag and see if that cleans it off. But we are not scraping into the surface paint of the wing to go ahead and get this frost off so we can make the flight today. Cool. Now we have icing. Now per our aircraft's pilot operating handbook, flying into known icing conditions is prohibited. So we're never flying into icing conditions because we have no, really nice anti-ice de-ice equipment. We do have anti/de-ice equipment, but we don't have those big de-icing boots on our aircraft. Icing's going to do a few things. It's going to add weight. It's going to change the aerodynamics of the wing, and it's going to make seemingly safe airspeeds unsafe. If we're ever approaching to an airport and we suspect that we have some sort of ice on the wings, we're going to fly a faster airspeed than usual. It'd also be recommended not to use flaps as well because you don't know what the flaps are going to do. So fly a little bit faster if you suspect you have ice. 2 conditions have to happen for icing conditions to form. So first one is going to be visible moisture. And then the second one is going to be below freezing temperatures. So you can kind of imagine if we're doing a cross country, to Tucson, and we're IFR rated, and we want to go ahead and fly through the clouds today. Well, is it below freezing temperatures today at altitude that we're picking? It is. We'll probably get some icing conditions. That's known icing conditions there. So we need these two things: visible moisture in the form of a cloud, any sort of rain, fog, anything like that, and then we need below freezing temperatures as well. We're going to have 3 different types of icing. We have rime, clear, and mixed. Rime ice happens between -20 to -100 degrees Celsius, or Celsius there. And then we have, for clear, -10 to 0 degrees Celsius. And then for mixed ice, we have -15 to 8 degrees Celsius. So rime ice, this is going to be small ice droplets that don't have a lot of time to spread out and form onto the wing. So if we go up in altitude, there's going to be what we call supercooled water droplets. So what they need is a condensation nuclei to actually form into ice. Yeah, we have these water droplets at atmosphere that are past below freezing, but it's still water. Why is it not a solid yet? It needs to come into contact with something. It needs a condensation nuclei to actually form as ice. That if you think about putting a water bottle into a freezer for hours, it still stays into the form of water, but if you tap it, if you throw it on the ground, it turns into ice instantly. So it needs some sort of catalyst to actually form ice. What's a perfect catalyst for that? Your aircraft. So rime ice, it's going to be smaller supercooled water droplets hitting the leading edge of your wing as you're flying through visible moisture, creating little droplets, and they're actually really easy to see. Clear ice, however, are bigger supercooled water droplets. They have time to spread over the aircraft, and you can't really see it, which is why clear ice is going to be the most dangerous out of all 3 of these. And then mixed ice, you can guess, it's going to be a mix of super big, super cool water droplets and really small, super cool water droplets. Thing that you will be asked in your check ride, which one is the most dangerous? It's going to be clear because we can't see it. Do we have any anti-ice or de-ice equipment on our aircraft? We actually have 2. We have pitot heat. So heating up that pitot tube so it doesn't freeze over. Not only is that de-icing, if we do get some sort of blockage there, it is anti-ice. So if you suspect you're flying through some sort of icing conditions, turn that on and try to prevent it. We have also windshield defrosters. Those inlets on on front of the, we look at our steam gauges on the mount behind that, just aft of the engine cowling inside of the aircraft. We have those outlets that shoot heated air onto that windshield. That is anti-ice and de-icing equipment as well. Biggest thing, the hazards degrades performance, especially with induction icing. With the fuel injected system, you don't really get that. You could get icing over your air intake, but that's going to open up your alternate air door, and you'll probably experience at least a 10% loss in performance there. Drastically reduces lift, changes the aerodynamics of the wing, increases weight of the aircraft, just making seemingly safe airspeeds unsafe. And now let's wrap this thing up with fog. So fog, sorry, had a little break in the video there again. We're just pushing back towards fog, which will be the last section we go ahead and cover. Fog is going to have no difference between clouds at altitude and clouds close to the ground. Fog is going to be clouds close to the ground. They try to define it less than, I think it's 50 to 100 feet. You can double check that. But it's just going to be a cloud that forms, usually because of the relationship of the ground cooling at night or cold surfaces coming into contact with moist air. If we think about frost and dew, basically the same thing, except this isn't happening in below freezing temperatures for frost. This is above freezing for the most part, unless we get into freezing fog, obviously. But the first one here is going to be radiation fog, which is kind of how that frost actually, develops on our aircraft on, calm, cool nights. So we have the surface at night radiating all this heat into the atmosphere, and we have all these air parcels that contain moisture above it. This ground gets super cold, a lot colder than the air above it. It cools, condenses the air parcels above it, and then we get condensation. We get some sort of precipitation, some sort of visible moisture over the ground. This has to happen on cool, calm, clear nights. No wind involved in this one. The one that involves wind is the next one, advection fog. So advection fog happens when air pushes a warm, moist air mass over a cold surface. So we have cold ocean water here, and then we have land. We have this warm, moist air being pushed by the wind over this cold surface. As it goes over this cold surface, it cools that air mass, and then condensation occurs, and that's where we get sea fog. The next one here is going to be upslope fog. And this kind of is very similar to, that orographic lifting. So we have an air mass here. And it's being pushed by the wind up the topography of the land. What happens as we go up in altitude? It gets cooler, cooler, cooling the air parcels, condensing it, and that's where I get some sort of fog over mountains. Next one here is going to be precipitation induced. This is going to be warm rain falling through a cold layer, a layer of the atmosphere. So we have this rain here falling through a cold atmosphere. It's basically going to create some evaporative cooling. So if we had a really hot pot of coffee and we poured it on a cool surface, it goes ahead and evaporates these air molecules, putting them past their dew point, and condensation is going to go ahead and occur. That's why if we get a lot of rain on, if you go to Europe, stuff like that, very wet, moist areas, when has a track record for a lot of rain, we get some sort of precipitation and induced fog with it, warm rain falling through a cold air mass. And then we have steam fog, which is going to be kind of, if we imagine this over open water, cold air moving over warm water. So we have warm water here, and we have this cold air coming in contact with it, kind of the reciprocal of that hot coffee situation. If this cold air, this cold surface almost, if you could imagine it, coming into contact with the cold, with the warm water, we get evaporative cooling, and then we get that sea fog or steam fog over the water. And then we have the last one here, which is freezing fog. Let's see if I can find some space up here. Which is going to be basically radiation fog and below freezing temperatures. So where frost actually occurs, we get super cooled water droplets in the atmosphere as well. So not only do we get frost on the objects on the ground, we also get water droplets or air parcels that have water in them that lack the condensation nuclei to actually form as frost onto any surface. So freezing fog is radiation fog just happening in below freezing temperatures. If we go ahead and go into a place that has some sort of freezing fog, when we come into contact with it, it will form as ice onto our aircraft or car, wherever it is. This is usually happening at very low altitude, so it'd be more likely it's your car. But yeah, that's going to be the different types of fog there. So we covered, we went over different types of fronts, how frontal lifting actually takes place. Just make sure you understand those surface analysis charts. Go ahead and look at those and get those color identifiers for it. Then we went over thunderstorms. We went over frost, the different types of fog as well, and the different types of ice. Each one has its own different hazards associated with it. This all goes back to your go or no-go decision, your 91-103 pre-flight action, NW craft, the acronym for that. First one's going to be NOTAMs. Second one's going to be weather. We have to be familiar with all the weather pertaining to our flight. To go ahead and understand that, you have to have a good base in weather theory. To go ahead and actually dissect these charts is going to be, weather information, which we're going to get into next. But that really ultimately goes down to your go or no-go decision. Do I have to make this flight today? Most likely not. So live to fly another day. Make sure you understand this weather theory, and make sure you're keeping you safe and your passengers safe as well, so you don't experience any of this stuff going on. Thank you so much.